not going to complete section 6.3. This is the third video in the series for chapter 6. And quite honestly, the most important one relative to your project. I'm going to make some comments about how to do a distance learning completion of a project that required a face-to-face survey. So let's push through the material that we need in order to complete the calculations, and then we'll talk a little bit about how we're going to make some changes to the way you're going to go about collecting your data. So 6.3, proportions. Well, a proportion comes from a binomial variable, and as you know that a binomial variable comes from a scenario where we can only count what? The number of successes. So we define what success is, and the value that x takes on is a function of the number of successes. The point estimator is no longer x bar. That was the arithmetic mean for a continuous variable. We dealt with that in 6.1 where sigma was known. We dealt with it in 6.2 where sigma was unknown. But these were what? Continuous random variables. We're now dealing with a discrete scenario, and not only is it discrete, it is binomial. So the point estimator for the proportion p, the percent of success, remember I've asked you to already hypothesize in your mind for your project, what percentage of the people that you asked do you think would agree with you or would affirm the success? So we're going to now create confidence intervals that allow us to make statements about how confident we are that we have found the appropriate interval that's going to surround that population proportion. So the point estimator, we put a little hat on the top of the letter P. It looks like an inequality symbol turned on its head, and we literally call it P hat. And then we have its complement called Q hat. Again, nothing has changed. The sum of the probabilities and the probabilities distribution for the binomial scenario is still 1. So Q hat is still going to be 1 minus P hat. That has not changed. So P hat, again, is a ratio, and it comes from the number of successes out of the sample size. Here's the good news. We're back to normal distribution techniques here. We're not using t-distribution like we did in 6.2. The only time we're using t-dist is when we don't know the population standard deviation and we're working with this continuous variable. We're back to binomial. Now, we're not worried about what? Central limit theorem any longer, the n greater than or equal to 30. However, we are going to ask ourselves the same questions that we were asked before. Only this time, when we're working with sample data, we're asking ourselves, is n times p hat greater than or equal to 5, and is n times q hat greater than or equal to 5? So that's sample size times the number of successes in our sample, and sample size times the number of failures. If both of those are greater than or equal to 5, then we get to proceed. Again, the confidence interval that we're creating will be surrounding what we hope is the population parameter, and we're using the p hats, plus the margin of error and minus the margin of error. Well, what is the margin of error? Well, this time, it's back to the normal distribution. Love that. So again, if it's the 90, the 95, or the 99, it's 1.645, it's 1.96, it's 2.575, and in your project, I've asked you to stick to those industry standards. So that's good news. You already know what they are. I want to ask you, though, to take a good look, because this is kind of different. In your textbook on page 321, I'm not going to hold you accountable for being able to create the derivation, but the derivation is there. It takes us from sigma p hat equaling the square root of pq over n. It shows us where this came from. So again, we're going from known standard deviation of the population at what? The square root of npq, and we're now deriving in terms of our sampling scenario. So that's where this comes from. Again, another quantity for you to hold on to. On the bottom of page 321 are our steps to success. Again, these are going to function exactly like the others. with the exception that we are now working with a population parameter, which is a proportion. It is not mu. It is not a mean for which x bar is the point estimator. We're now working with a population proportion p for which p hat is the estimator. So for the sample data, find p hat. You have to find it. And then make sure that this is true and this is true. If it is, then go ahead and find the margin of error. And you can do the calculations. Assuming you know C sub C, no problem. Now, take a look at the study tip on page 321. Here we go again, lucky us. We have a lot that's already been provided to us in the calculator. If you hit the stats button and you go over to tests, this time you have to arrow down because it's not going to appear on your initial screen. You have to find item number, I believe it has a letter actually, A. Yeah, it's A. It's 1 proportion Z interval. 1 proportion Z interval. This is item A. One proportion Z interval. If you choose that, again, it's going to ask you to put in X, which is the number of successes, N, which is the sample size, and the confidence level. So just as it's indicated in the box there, and hit calculate. And it's going to do the work for you. But the arithmetic that's involved comes from using the Z sub C, the critical Z, per the confidence level, and the p hat and the q hat that you have derived from your study. Much like we did in 6.1, we can come upon a problem that says, well, what would be the minimum sample size in order for me to meet a particular set of criteria? So if you would fast forward with me over to page 324, you'll find the recapitulation of the error formula, this time solving for n. That minimum sample size, it's going to guarantee the success level that we're looking for. So, I will say that there is an oh by the way. There's an oh by the way. This formula assumes that you have preliminary estimates of p hat and q hat. If you don't, then you would start with an equal distribution of 0.5 and 0.5 for p hat and q hat. If there's not information provided to you, you would use p hat at 0.5 and q hat at 0.5. That's at least a starting point. It's as unbiased as we can be with regards to giving weight to number of successes versus number of failures. So again, to find confidence intervals using proportions, again, it's a situation where we have binomial type problems. So we're counting the number of successes divided by the sample size to give us that point estimator, that unbiased point estimator. We're going to call p hat. We know its complement q hat is 1 minus p hat. This time the margin of error, assuming that what? NP hat greater than or equal to 5 and NQ hat greater than or equal to 5. The margin of error calculation then is Z sub C coming from the normal distribution table or from the calculator with P hat, Q hat, and N all under the radical. The radical belongs to the entire ratio. Adding that on the positive, subtracting it from the, for the lower bound will give us the appropriate interval. Now, let's talk a little bit about what's coming up. Due the 27th, yeah, today, page 325, numbers 3 to 21 odd. So these are problems directly from the textbook. Again, you can check your answers. But I want to talk a little bit about the project. Over the weekend, because we're coming close to the end of the term, as you know, and I believe I had an April 3rd date due for the project. What in the world are we going to do? We're not here in school. Oftentimes, when statisticians are unable to reach the sample in the way that they would like to, they create something called a simulation. Again, a simulation is supposed to model reality, but it isn't real. Yeah? So this is what I would like for you to do for your project. I would like for you to complete a simulation. I would like you to find a fair coin. I'm sure there's some coins in your house. Choose a coin. You can define however you want. Heads is success, typically tails is failure. I want you to flip the coin 75 times. And I want you to record your results. If the flip of the coin, if the trial indicates heads, you check off that that person would have agreed with you. If it lands on tails, that person would have disagreed with you, which would have indicated a failure. This is where your P hat and Q hat are going to come from. So again, you flip the coin 75 times, simulation of your survey. Use those numbers for P hat and Q hat in your calculation for confidence intervals. Now, if you look at your project sheet, the levels were at 90, 95, and 99. We know what the Z-scores are, 1.645, 1.96, 2.545. By the 31st, I would like for you to have completed your simulation and calculated those 3 confidence intervals. Please send those to me on the 31st as your homework. I'd like to take a look at those, and then we'll move forward as far as interpretation of results. So this ends our discussion of section 6.3.